Now, let's gear ourselves to something with the electrons and things called valences. Again, there's our electron, or I'm sorry, your atom, and the things swirling around are going to be your electrons. We have this electron cloud, and the thing is, we can't say where the electron is precisely, because it's moving all around. We could just say it's in a certain cloud, it's in a certain area. But we can't predict exactly where that is. So we sometimes refer to it as the electron cloud. But there's different layers. You see there's different, like there's a loop here and a loop here. Yeah, and technically, this would, if they're all the same size, that would be wrong. It should be small, like a bullseye kind of thing. So anyway, the electron cloud is the area where the electrons swirl or spend most of their time. And this determines the reactivity of an atom. We have these electron shells, layers that hold a limited number of electrons. So each one of these little circles over there can only hold so many electrons. They hold less, but they can't hold more than what they are. And I'll show you which ones. The number of shells per atom corresponds to that row or that period on the periodic table. I'll show you where that is again on the periodic table. So there's clues on the periodic table that will help you. Each cell is an energy level. All right, a potential energy. Energy that can become kinetic energy. It's potential. It's getting ready to burst, right? The lower shells closer to the nucleus is going to fill first, and then they get further and further away from the nucleus. The outermost shell has the most potential energy. The outermost shell can only have a maximum of 8 electrons. You have less, but once it's 8, it's filled. It wants to get filled. Because once it's filled, it can't react really. So if there's only 7 there, it's ready to do something. Once it gets something, another atom or something. So this is just showing you, as we go further out, here's the nucleus, if it goes further out, energy, it wants to release energy. It wants to bring in, like the highest energy level, potential. It's going to be furthest out there. The lowest potential energy is going to be inside here because it's already filled. It gets filled from the inside out. Once the inner layer gets filled, it jumps to the next layer and that fills up next. And this is just giving you some examples of where that. Now, the shells have names to them, M shell, L shell, and K shell. I'm not here for you to memorize all that. It's chemistry. But it just tells you here that the first shell, 2 electrons is the maximum. Second shell, 8 electrons. 3, another 8 electrons. 4, 18 electrons can go in it because they're getting bigger, these shells. The numbers you should memorize. That's not too bad. But don't worry about the names. But the key also here is that the outer shell of an atom, no matter what letter, can only hold 8 electrons. And I'll show you what that means. The valence electron is that outermost shell. Okay? Valence electrons, those electrons in there, in that last outer shell, we just refer to them as valence electrons. And electrons, though they can have a maximum of 8 electrons, as I just mentioned. All right? With the exception of helium, because it's such a smaller atom, it can only hold 2. Atoms are most stable when the valence electron or valence shell is filled. Once it's filled, it won't react. It doesn't need to react. It's filled. It wants to get filled, so once it's filled, it's filled. So atoms will react with the other atoms to fill that outermost shell. This is where the bonds come into place. Okay? Element. They're also known as the noble gases. But the inert elements have their valence electron, the shell, filled. And they call it inert because it can't react. Although recently they found that they got to push themselves and they can slightly react. But for this class, inert gases or inert elements, they can't react to anything. All right? It's difficult. And they're actually on the last column of the periodic table. All of those down there, including helium, neon, argon, and so forth, are going to be these inert gases, or noble gases. So, let's just do a little catch-up over here. The period is the row. These are rows going horizontally. Columns are going down. Okay? The period, each row, this is the number of shells per atom. There's going to be 1 here, there's going to be 2 shells here, 3 shells here, 4 shells here, and so forth. And that's what's happening. Does that make sense? Pretty straightforward. I'm going to give some examples over here. The noble gases, those inert gases don't react to anything. They're the ones over here in blue, with helium, neon, argon, and so forth. They can't react to anything. Those are our noble gases. Their valence electron shell is filled. Now, looks busy on here. Don't expect you to know all this. But what I'm trying to show you here is that helium, the first one, if you look at this box over here, these are the number of shells. So first shell, second shell, third shell. In helium, there's 2 that I can fill up, right, for that first one. You can't put any more because it's a small atom. So it's inert, it's filled. Whereas hydrogen is not, it only has 1. It has the capacity to get another one. Neon, once it fills up 8, it's now inert. It can't react to anything. And you can look this out with yourself. It's just showing you the same thing, the first cell, second cell, third shell. You can see where all these come in, and you can look at all the different ones on here. Again, I'm not here, it's not for you to memorize, but I want you to understand the concept. Now, let's talk about ions. Any questions about anything so far? No? Okay. All right, ions. Electrons. Now, keep in mind, like I said before, an electron has a negative charge. Something's going to get a little confusing. They have a negative charge. An ion is an atom that either gained an electron or lost an electron, based on what I explained to you about valence shells, right? The last outer one. You can add something to it, you can subtract something to it. Now, a cation has a positive charge to it. This means, this is where it gets confusing, but I'll show you something on the board to make sense. If you lose an electron, it becomes positive. Right? We call this oxidation. You lose an electron, it becomes positive. Half of you may understand what's going on. Half of you is like, that's the opposite of what I've known all my life. Right? You lose, why are you positive? Well, you could also have an anion, and that's when you gain an electron, but you become negative. And that's what we call reduction, because you're reducing it, right? Reducing the charge. So this is why. And I'll show you up on the board here. Let's say we have, and keep in mind, electrons are what kind of charge? Negative. Okay. So we can have let's say an atom that has, let's make this stable. So we have protons and electrons. And this is stable at this point, right? 5 and 5. Okay, fair enough? That's stable. But look what's going to happen here. If we, so right now the charge is 0. You agree with that? Yeah? Okay. Now look at this. I'm going to lose an electron. Right? If I lose that electron, does this become positive or negative? Negative. Look, you got 5 positives here, you got 4 positives here. Does that make sense? Right? Clear about that? This is a cation. You lose an electron, you become positive. Okay? Likewise, you know where I'm going with this. If I add an electron over here, it gains 1. Does it become negative or positive, this atom? Negative. The key is the electron has a negative charge. Don't forget that. Think of a happy cat, a positive cat. A cat ion, a cat is positive, right? Or if you want to think of a cat ion, you got this positive here. Whatever you use for your mnemonic. But mnemonics only work for a certain way. You need to understand the concept, because that's not going to help you if I ask you if it's going to gain or lose an electron. But are we clear about that? It took me 7 years to come up with that concept to help students understand it. And it just, everybody understood it. All right? Is that clear? Good. All right. Now, so this is just showing you the same thing. If, the atom loses an electron, it becomes positive cation. If it gains an electron, it becomes an anion, a negative. Okay? Now, we have ions in the human body. All right? Now, there's cells, and we're going to get into cells later on. But I really want you to have this memorized, because if any of these are going into further things and you start learning about something called an action potential and things about membrane potentials and dealing with cells later on, you need to understand this, at least in the human body. Inside the cell, we call it intracellular. Inside the cells, the major cation in what we call ICF is going to be potassium. The major anion is what we call a phosphate. And that's how you abbreviate that. You'll learn about those later on. Outside the cell, the major cation is going to be sodium. And the major anion is chloride. And the extracellular, outside the cellular. So here's another little mnemonic I used to give my students. The salty banana. Think of the banana as your cell. What is the banana loaded with? Potassium. So inside the cell, it's going to be loaded with potassium. But then you have this putting salt on top of it. What do we know is salt? Sodium chloride. So you're going to have a lot of sodium chloride on the outside. The only one you got to memorize is phosphate. I think that's a little bit easier to manage. Now, one other thing I just want to say, and I'll finish this topic. I am not saying that potassium is only found inside the cell. There is potassium on the outside. It's just there's more potassium on the inside. Likewise, sodium chloride. There is sodium chloride inside the cell. There's just a whole whopping amount outside the cell. And that's going to be important when we've got to deal with diffusion later on. We clear with that? I'll get back to salty banana maybe later if you're going to take A and P and stuff. Okay? That's what I'm talking about, my art therapy. All right? And different ways to memorize things. I'm just trying to gear you to try and come up with these different weird ways. And when you come up with mnemonics and come up with these stupid things up here, who cares what's in your head? If you think it's really stupid and you don't want other people, that's fine. It doesn't matter. It's whatever works to help memorize for you. Everybody's different because you all have different experiences. It doesn't help you if you come from Alaska and never ate a banana in your life. This won't make any sense to you. I think everybody ate a banana here. Right? So I'm trying to open those hidden gems that you guys have in your brains that you did not release yet. Just do it. If something's ridiculous, you'll remember it. Okay? All right. So let's start a little bit about chemical bonding. Okay? Chemical bonding. We have chemical bonds. Putting elements or atoms together to make molecules and compounds. All right? Then we have these interactions. A molecule is the unit of atoms forming this interaction. And the electron is what's going to be doing this work. We have three types of bonds. Ionic bonds, covalent bonds, hydrogen bonds. All right, we have James Bond, but that didn't fit. These are our three bonds. And there are subtypes of those too. But there are three major bonds. Some are very strong, some are not so strong. They'll go strong, not as good as superglue. Maybe you want to staple something, put tape on it, right? We have different bonds that we can do. So we have ionic bonds. Ionic bonds is an attraction of a cation and an anion. These are kind of like magnets. And you can pull them apart if you're strong enough. Okay? But this is an exchange of one or more valence of electrons. An exchange of them. These are weaker than covalent bonds. Because you can pull them apart. There's things that could actually make them come apart. We call these ionic compounds salts. Now, I don't want you to think that sodium chloride is the only, it is a salt, sodium chloride. But we have other salts than just that. Potassium chloride, magnesium chloride, there's a bunch of other ones. So the example is my sodium chloride over here. All right? But it's an exchange of one. Kind of like this little video, right? Exchange. Exchanging the red one for the yellow one. Exchange. And you can pull them apart though. Then we got covalent bonds. Covalent bonds is a sharing, not exchange, but a sharing of one or more valence electrons. Now, this is the strongest of all of them. This is the superglue. And you can take superglue and put acetone to it and break it up, but you've got to do some chemical stuff to really do it. You've got to put some energy to do that. They can break, but this is the strongest of them all. Water is a good example of covalent bonding. The thing I drew up earlier, the two hydrogens bound to that oxygen. When I drew those little lines in there, that is a covalent bond with each other. We could have single covalent bonds. We could have double covalent bonds, as I showed you with oxygen. And there's two lines there. We could even have triple covalent bonds, and that's what nitrogen gas is. And it's doing that, right? When you share something, you don't want anybody else to share it with you. You exchange it, well, you exchange it, then it's up to that person who wants to give it off to someone else. But if you're sharing, you don't want anyone else to share things with you. So that's our single covalent bond. You can have one, that's carbon, and then you got 4 hydrogens over here. Carbon has 4 electrons in its valence shell. That's a key thing. Carbon's going to be very important talking about the rest of this course. There's a double covalent bond, as I showed you with oxygen. And nitrogen has the triple. So they're sharing 3 pairs. Not 3 electrons, 3 pairs of electrons. Which brings up the topic of something called electronegativity. It's the attraction of electrons between 2 atoms connected with a covalent bond. The more electronegativity an atom has, the more strongly it is pulled in the shared electrons towards itself. Stronger electronegativity means a stronger bond. We could have something called nonpolar covalent bonds. If the 2 atoms are the same, and they're sharing it equally. Like the tug of war, it's at a standoff. No one is more powerful than the other. Hydrogen gas, which is going to be H2, is out there. It's like that. Oxygen, O2, it's like that. Those are nonpolar covalent bonds. Well, you're going to see, we're going to spend a lot more time talking about also these polar covalent bonds. That's if the 2 atoms are different. Sharing of electrons is usually unequal. Water is like that. And that's ammonia, right? NH3? I think it's ammonia. The exceptions are carbon dioxide and I think it's methane. All right? Because carbon and oxygen have the same strength of each other, they tend to be nonpolar. So these are the exceptions, okay? And it's just showing here a water molecule, which is polar. Oxygen is going to be pulling on these 2, but they're unequal. This is what we call a partial electronegativity, partial pressure coming onto there. So this has a negative partial over here, and these 2 would have positive. So they're polar. It's not going to be equal. We're going to get into that a little bit more. So we could do, methane was ammonia. So we have methane, ammonia, water, carbon dioxide, and you can see what they kind of look like. We'll show you in another lab later on, putting together some of these molecules so you see it. We'll have you guys do that. I'll have some that are already set there so you can see. Maybe I'll just bring it in here too and just show you what they look like. Because they're really a 3-dimensional thing, and I want you to appreciate what double bonds do too. But you can see carbon, how they drew water? It's polar. You can see the way it's bent like that. Whereas carbon dioxide, they're equal on either side. That's a nonpolar thing. They draw it like a straight line. So when we increase the strength, ionic bonds, then polar covalent bonds, and the nonpolar covalent bonds are the strongest that we have. That's an increase in strength that's going on there. Let's talk about hydrogen bonds. And this is what the whole next chapter is going to be about too. Hydrogen bonds. They're very, very weak bonds. They probably have about 5% strength of a covalent bond. They're very weak. We could break those. They're responsible for surface tension in water and a bunch of other properties that water has. Those things I was telling you about how water floats and how, or I'm sorry, ice floats in water, or how you put a bottle of water in the freezer and it expands. Like, we're going to talk about those later. So hydrogen bonds form between a slightly positive charged hydrogen, and a slightly negative charged atom. And it's usually oxygen or nitrogen. All right? In what we're going to be talking about. All right, examples is water and ammonia that do this. So there's links between the molecules or between distant parts of a large molecule. And these large molecules can be very, very big. So we have things called intermolecular bonds. They're attracted between two molecules. And ionic covalent bonds are what we call intramolecular. So let me show you something between the two here. Water molecule, right? Water molecule, right? Water molecule. Water molecule. What kind of bonds are these? Be careful. What kind of bonds are these? Hydrogen, covalent, ionic. What kind of bonds between an oxygen and a hydrogen in the molecule? Covalent. Right? That's what I showed you before. These are covalent bonds. What I'm going to show you now in red is that a bond, a weak bond, between two molecules, a hydrogen and oxygen of two different molecules, that's a hydrogen bond. This is a hydrogen bond. This is a hydrogen bond. Intra, you got to be careful with these words, intramolecular bonds. Intra means within a molecule. You have intramural sports, don't you? Right? That's where the science department plays against the English department in a basketball game. It's within the same school. Intramural. Intramolecular are bonds within the same compound, right? Is that clear? Covalent bonds are intramolecular. Intermolecular are bonds that are hydrogen bonds in between two different schools, two different molecules. See the difference? Okay? This helps create a three-dimensional structure. You're going to soon find out that this is going to be why ice kind of stretches, expands, the structure of it. It's because of these hydrogen bonds. When we talk about DNA, DNA is held by hydrogen bonds. They're easy to break. We're going to talk about that zipper-like thing later on. Yes, intermolecular. Intramolecular are these black ones because it's within the same. Here, if I draw that's one molecule of water, right? So the bonds within that molecule of water are intramolecular, right? Like intramural sports. So this is intramolecular, which are examples of covalent bonds. When we're dealing with intermolecular, they're within two different schools, two different molecules. And those are going to be your hydrogen bonds. Okay? Yeah? Well, they're partial. It's because of electronegativity. What do you mean? Well, these are bound together because the electrons themselves, they're being shared. Whereas the electrons over here, they're not being shared at all. They're just touching each other. Does that make sense? Okay? Is that clear? All right, but it helps to form this three-dimensional structure too, which you'll see later on. All right, so again, what's happening up here? All right, here's the oxygen. You have a sharing of electrons here with the hydrogen. You're sharing electrons over here. This is going to be slightly positive over here, slightly negative. That's electron negativity. Makes for a polar water molecule. But like I said, there's a molecule of water, there's a molecule of water. The hydrogen is going of one molecule will form a hydrogen bond with an oxygen of another. Not a hydrogen of another, an oxygen. Hydrogen is positive, oxygen is negative. So they'll attract that way. Kind of does that. See, it's forming like a three-dimensional kind of figure. Okay? Again, what I kind of showed there. There's our covalent bond of a water molecule, oxygen and hydrogen. There's another water molecule, but the attraction between the two. And please don't get this mixed up. That it's hydrogen of one molecule with an oxygen of another. Not hydrogen to hydrogen or oxygen to oxygen. All right? And it could get really big, which is a whole chapter right after this. All right? So the bond strength, hydrogens are the weakest, then it's getting stronger is the ionic, then polar covalent bonds, and then nonpolar. Nonpolar covalent bonds are the strongest. Hydrogens are the weakest. Little chemistry geek kind of fun. Caution, what for? Supposed to get a laugh, okay. All right, so let's start talking about molecular structure and functions. Okay, so structure versus function. Function reflects structure. This is a running theme that's gone throughout all of biology and chemistry and, especially when I do anatomy and physiology. Function reflects structure. Meaning, the way something functions is usually because of the way that it's shaped. Right? We can hear things pretty good because our ears are like a funnel. So kind of the sound kind of goes in like a funnel. We can hear in stereo things in front and in the back because our ears are located on the sides of our head. If we had our ears, and maybe that's the way it was in caveman time, I don't know, but maybe if they were in the front of our head, we could hear very well in the front, but we're going to miss out on a dinosaur that's going to chomp us from the back, right? So, and in natural selection, those cavemen probably died off, right? So, the way something functions is because how it's shaped. If I take that clock up there, I mean, looking on the front there, you see they're all going clockwise, and one's going faster, and one hand's going faster than the other. But if you look in the back, the way the gears are made, it's because that's how it's functioning, is because of the way the gears are in the back, right? So that's why these molecules have to be shaped in a certain way so that it can function properly. If they don't, they're going to break off or cause disease, and maybe those genes will eventually die. So it has to be made a certain way. The shape of a simple molecule is governed by the geometry of the bonds. Hydrogen bonds and covalent bonds and ionic bonds, they all will put the shape together. Nitrogen and carbon dioxide are linear, meaning straight. You see that, the carbon with the two oxygens on the sides. It's a linear thing. Methane, however, which is CH4, is more of a, almost looks like a pyramid. That's why if I had models here, I would show you. It's more 3D, and we call it a tetrahedron. Water is planar, meaning like it's flat, but it's also bent. It's kind of like doing this kind of thing, like a wave. And it's because of the two unshared electron pairs. So, you know, the oxygen is slightly more negative, and the hydrogens are slightly more positive. So this is all going to change, or these shapes are all going to determine how they're going to function. This is what I'm saying by the tetrahedron, where it's kind of like a pyramid. One goes down here and over here. But even if you turn this on the side, this angle is the same angle as this. It might not look like that because of that, but that's why these little molecular Lego things that we have, you can actually see what that means. Just kind of showing you like that. They all have certain angles. I won't ask you about the angles. That's chemistry and further courses in chemistry. But understand, they have set angles, and it creates this three-dimensional thing. And this three-dimensional thing, the way they're shaped, is the basis of biology, the basis of everything. For instance, this is a cell, a certain cell in your body. Here's the cell membrane, a membrane that kind of holds the cell together. We have a natural endorphin that cuts down on pain. And you could release these endorphins when you exercise. You feel happier. Releasing these endorphins. And they attach to the receptors and make you feel happy inside. And you don't feel the pain. We've learned about what that structure of that receptor looks like, and we know what the endorphin looks like, the part that binds to it. And pharmaceutical companies take advantage of that with the chemists. They make loads of money. And why don't we make it some kind of substance that has this same thing, but yet this is going to be different? a synthetic thing. Lo and behold, morphine was born. So now, people who have cancer and have a lot of pain, we could give them morphine and they won't feel the pain because they go on endorphin receptors. So understanding how structures are tells us the function. But later on, you can make the big bucks and learn how to make that portion of that structure to go on that receptor. Many ways. I would say about 80%, if not more, of the drugs that are out there, medications and stuff, are worked on this same basis. Okay? Chemical reactions. I'm going to be very brief with this, and we'll get into the heavier stuff later on. A chemical reaction is the process that forms or breaks these ionic or covalent bonds. They're symbolized like this. Reactants going to products. This is a yield sign. Going from reactants to products. Hydrogen plus oxygen, we get a product of water. We could also have the yield sign going both ways. So if we put more stuff here, the reaction will go this way. If we put more stuff here, the reaction goes this way. This only goes one way. This makes this an irreversible reaction, whereas the other one is a reversible reaction. If you put everything in here, on this side, all of it becomes the products. You put more products over here, it's not going to go back the other way. We're going to talk about this later on. There's something called Lachadier's principle. It's the basis when we deal with carbonic acid. So we have three different main classes of reactions. Where they break up. And it's going from large to small, right? A, B, to break it up to A plus B. We can have synthesis, the opposite, right? And that's going to go from A plus B equals a combination, AB. Or we can get a little funky over here, and AB plus CD maybe have a little intermediate, and now the C can come off of this and go here, and B can go on here like that. All right? And that's more an exchange. We could have steps within steps of that. Okay? And this is just showing you decomposition, synthesis, and exchange, right? Going from a large starch molecule like potatoes and turn them into smaller glucose things that we can use to make energy. Or we take amino acids and make a huge protein. Or just doing something like that, which there's a lot of, there's not really an example. So now does this make sense? I'm hit, I've lost an electron. Are you sure? I'm positive. Now I get the laugh. Okay, good. Okay.